matrices, and then what you do is simply you calculate the Pauli expectations of the Pauli terms individually, and the summation with that coefficient can be done classically. So what is the point here? Why am I emphasizing it so much? Is because there are two things that can happen. First, as I said, that you may want to have a probability distribution. Algorithms like Shor algorithm, Grover algorithm, these are the algorithms where you need the final state. Or even if you are doing quantum communication, I am talking with you, you want to know what I am saying and you don't want to calculate some expectation value of what I said. That makes no sense, right? So there are scenarios where you need the exact state after running a circuit. There are again many scenarios, say you want to calculate some energy of molecule, you want to, in machine learning, you want to find out some accuracy, you want to find out some graph properties. All of these can be represented as some observable. When we talk of error mitigation is applicable in this domain. It is not applicable in this domain. So whenever you need the state as the outcome, error mitigation is not applicable there. So henceforth, don't think that in quantum communication we can improve using error mitigation. That's not going to happen. Now, what do we do with a quantum computer? We will stick to the expectation value picture because that's where error mitigation works. So this is a general quantum circuit. It's a GHZ circuit, but that's not very important here. Ideally, what we want to do is we run the circuit, we get some outcomes, and from there, for some observable O, we want to calculate the expectation value. This is ideally what should happen. But what ends up happening is nothing is perfect in a quantum computer. So if you ask me that can you prepare the qubits correctly? No. I don't guarantee that the qubits are always prepared in 0. That's not guaranteed. When I am applying the gates, can you guarantee that the gates are perfect? No. I don't guarantee that. The gates also have some noise. There are some errors when you are applying the gates. Can you measure them correctly? No. Even when we measure, there are some errors associated with it, and even when you are not doing anything, the qubit is sitting idle, it has a tendency of relaxing and going down to the ground state. So when we actually run the circuit on a quantum computer, we get something apart from what was expected. We expected these two outcomes, but we get some other outcomes as well because of the imperfection in the quantum computer. And what we end up getting, if we calculate the expectation value here is what you think of a bias or some error terms that is coming into the expectation value. What error mitigation can do is, it can, using this information with some extra classical and quantum resource, it can give you an estimate of this term. This is what we want to do. Use it from this term, using a bit extra classical and quantum resource, we want to get to here. This is in one sentence what error mitigation can do. Great. So as I already spoke about that, the major hindrance, one of my colleagues actually did this poll on Twitter, that what do you think is the biggest hurdle for quantum computers today? Obviously the answer was noise. So this is a 156 qubit IBM Quantum device. It's IBM Pittsburgh. This is what the quantum computer that is coming to India next year is going to look like. Exactly, this is what it's going to look like. The characteristics can differ a bit. I don't know what it will be called. I hope it will be called IBM India or something. But here, if you see, there are a lot of noise here. As I said, readout. If you go to the IBM Quantum platform, you will find all the characteristics of all the hardware that are available today. What are the readout errors for each qubit? And you see that not only we have readout error, the error is pretty non-uniform. Some of the qubits have really high error, and these are kind of outliers, as much high error it has compared to the actual median value. When we try to run the systems, you see the lighter the color code is, the lighter the color, the higher is the error. So this is what the gate error looks like. This is what the 2 qubit error looks like. And you can see from here that roughly 2 qubits errors are way more, almost 100 times more than single qubit errors. And this has been true for all these IBM Quantum devices. So how do we address this noise? Of course, what we want, this is the final goal that we want to achieve, and in our roadmap, we have that to be happening first in 2029, and 2033 we will have pretty big error corrected fault tolerant quantum computer. The first one will come in 2029. That is of course the final thing to reach, where the errors can be detected that they have happened and I'll be able to correct it. Why is this useful? Because if I am able to do error correction and fault tolerance properly, I can suppress the error to any arbitrary low level that I am interested in. But at the same time, this requires a lot of resource. It really requires a lot of resource, and therefore the overhead that it brings is tremendous. And this is kind of the reason you understand that we all say that Shor algorithm can break RSA crypto system. It is not broken, because to break the RSA crypto system, the size of the keys that we have today, to factorize those, we need billions of qubits to ensure that it is error corrected. And if it is not error corrected, it's not going to work, right? So that overhead is there. But what can we do today? This is a question, what can we do today? And today what we can do is mitigation and suppression. It is not very important to differentiate between mitigation and suppression. It's kind of a term that we use, but roughly speaking, if you look into suppression, the errors are suppressed here during the execution without even detecting it. So one example is when you place your quantum circuit on the hardware, what you can do is, if I ask you that do you want to use this qubit or this qubit, all of you will say 22, because 23 has way more error. We can see it from this color code. So this type of selection, even before doing any computation or anything, this kind of selection where there is no extra quantum overhead, we call this as suppression. And mitigation will have some quantum overhead. This is kind of the differentiation that we do, but it's not very mathematically very strict differentiation, I would say. So in mitigation, the errors are modeled and then they will be removed as a post-processing step. It can extend the lifetime of computation, not to the level that an error correction will be able to do. It will be able to, but it will start requiring exponential resource, and at some point you will find that doing error correction is cheaper than doing error mitigation as the circuit starts growing bigger and bigger. Now, the other thing is, you cannot suppress errors to arbitrary low level. There are some error mitigation techniques, particularly PEC, we won't talk about this here, which actually allows you to suppress to arbitrary low level, but then the number of samples you have to do increases exponentially in the number of qubits and the number of gates, and it becomes like impractical at a very small scale even. It's difficult to scale it up. There is no extra qubit requirement, like in error correction, we need to encode the physical qubit into logical qubit, so we use multiple physical qubits to create a logical qubit. That does not happen here, but we do need to run the quantum system more time. So extra resource overhead is there, no extra qubit overhead is there. Now, if we look into what are the different types of noise, and as I wrote, this is a simplified view. Don't even think that these are the only types of noise, and these are not the only types of noise, but I'm putting in some of the noise that you can think of. So depolarization, over rotation, T1, T2 relaxations, crosstalk, state preparation, all of these kind of noise are there. And when we have all these different kind of noise, it's not possible for a single error mitigation technique to deal with all of these. So what we do in general, for state preparation and measurement, which we together call as PAM, we have what we call as measurement error mitigation. We will discuss this later, that in general state preparation and measurement errors are gauge equivalent, so you cannot really identify between both of them. So we usually say that all the error is in measurement. So you can always assume that. For T2 crosstalks, this type of error, you can do dynamical decoupling. Second thing that we do for all these kind of errors, including spam, is twirling. This is one of the major things that has done in current quantum computers, and we'll talk about what twirling is. And on top of that, we have what we really call as error mitigation, all these zero noise extrapolation, probabilistic error amplification, and all of these. What I intend to do today is to start from this side. So we will first make some approximations, some assumptions that certain things are really good, and we will start moving from here, and we will slowly try to do away with those assumptions. That's at least the plan that I want to do. Yeah, so any questions, comments till now? Okay. If not, let's dive into this kind of error mitigation technique. This is somehow, you will see, this is somehow very, very simple, and every time I see this, I feel like that this was invented before I started my career properly, but I wish I could have invented this. This is somehow very close to me for some reasons, I don't know. So the idea of zero noise extrapolation is, let's start with a bit mathematical, and then we will try to understand what each of these things mean. The first thing is, we know that in a circuit there is noise, and I am going to characterize that noise by some lambda 1. And we are not going to ask what is the physical interpretation of lambda 1, how are you finding lambda 1. We will just say, don't ask these questions. That's what we will say. Just assume that there are some way by which I can characterize the noise in the circuit, and I am going to call it lambda 1. Now this is called a noise factor, this lambda. Now I am going to create different noise factors, lambda 1, lambda 2, and so on, such that it's in kind of a increasing order. This we will see how we can do, even without explicitly knowing what is lambda, because you understand that it's not a very simple task to say that I have characterized the noise in the system. Even without properly characterizing, it's possible to increase the noise factor or the noise level. Now what we will do is, once we have a set of circuits which are functionally equivalent to each other but their noise level are different, once we have that, I am going to calculate the expectation value of each of them. And you can immediately understand that since each of them are in a growing noise factor, the noise is growing for each of them, the expectation value will be more and more away from the ideal value. Any operator you take, that's anything that you want to take, depending on the problem. Now if you think what we have here, so let's call this lambda 1, corresponding to that we have an expectation value. Lambda 2, corresponding to that we have another expectation value, and you see it is deviating away from the ideal value more and more because these are more noisy here. Now once we have this, we can just treat it as a set of data. We have a set of data, we need to fit a curve here, and then we just extrapolate it. This value E star gives an estimate of what it would have, what the expectation value would have been if there were no noise in the system. So just to again emphasize one point, this is in no way removing the noise in the system. I am not removing the noise in the system. I am using some extra resource to get an estimate what it would have looked like if there were no noise in the system, right? And you immediately understand from here why this will not work for a quantum state and why this will work for expectation values. There is an underlying assumption which I will kind of put away for now, is that the nature of the noise remains the same with increasing lambda. This, without this assumption, if you end up with, like, when you first increase it is increasing, then you increase it is decreasing, if it goes on like this, then it becomes very difficult to fit a curve. But let's put that aside for now and assume that this is what is going to happen. The nature of the noise remains the same. Now the question here is, how do you create these circuits, right? And as I said, that it is not easy to mathematically write down what lambda is going to be. So we cannot really expect to do that, but what we can do is, this is something called gate folding. What we can do, we know each of the gates are unitary operators. So forget about noise for the time being. If I take a gate U and I replace it with U dagger U, I have essentially done nothing. It is functionally equivalent, right? So if I replace this circuit with this circuit, in an ideal scenario, both of them will give me the same result. But the scenario is not ideal. So each of this circuit has each of this gate has noise associated with it. So when I repeat the gates 3 times, you can expect the noise has increased 3-fold. So see, that is how we do this lambdas. I haven't been able to characterize lambda. I don't need to. I will say that this is lambda equal to 1, whatever that means. I don't care physically. This is lambda equal to 3 because it has increased 3 folds. If I repeat this 5 times, that is lambda equal to 5. I can repeat it any odd number of times. It will work. And therefore, so we can replace a gate U with something like this, and then we can say that the expectation value looks something like this, right? As we start increasing, the expectation value is expected to go down exponentially as long as your noise model is either a stochastic Pauli noise model or even simpler depolarizing noise model. Then with increasing number of gates, it goes down exponentially. And we have already seen this, that from the points we get the noise factors, we run it, we get the expectation values, and we extrapolate it to zero noise limit. The question is that what will be the extrapolator, what sort of curve should I fit in? This is a question, what sort of curve should I fit in? And in general, if it is a depolarizing noise, it is obviously going down exponentially with increased number of gates and increased number of qubits. What? Yeah.
The whole block sphere will shrink.
Yes, yes. The whole block sphere is shrinking to the identity by 2. Yeah. So in general, you can always fit an exponential curve. That is mathematically correct. What is done in practice is, what is often seen, that if you try to fit the exponential curve, and then you extrapolate it, the standard deviation starts blowing off. So what is done in general is that you try to see that ideally if I can fit a linear curve, if the circuit is small enough, I try to fit a linear curve, that's better. Or even a quadratic or whatever, some polynomial curve, these are better. If none of them is working, you have to go to exponential, but often that becomes a bit of a challenge to fit that exponential curve and extrapolate. Now there are, so what we just told about ZNE, yes?
You assume a small noise channel for this movie,
Yeah.
right? But based on the platform you use, the channel changes a lot.
Yeah, so that's what I said, that let's keep that for the side, that, and let's assume this is
All noise is here only.
yeah, depolarizing or Pauli. It's also going to work, and we will address this. What you said, this is a valid question, we will address this. Yeah. So as you see, this is all about ZNE, and you can understand this is a very, very simple error mitigation strategy, and it's very intuitive how it works. It's very easy to implement, it's very intuitive how it works. But there are certain good practices and limitations for this. The first good practice that is done, it is done in IBM devices, is, as I said, that the 2-qubit gates are often 100 times more noisy than the single qubit gates. So in practice, often it is assumed that single qubit gates are noise free, only the 2-qubit gates have noise. This is an assumption that is made, and when you fold, the assumption is it's better to fold only the 2-qubit gates. It kind of restricts the depth of the folded circuit. That's one thing. There is another thing. Even after doing so, let's say that my original circuit has a depth of 20. And I fold with lambda equal to 5, now my depth becomes 100. What I mean here is a 2-qubit depth. What is 2-qubit depth? It's basically the depth of the circuit if you assume there are no single qubit gates. What will be the depth of the circuit? The reason we use this is the same thing, that 2-qubit gates are way more noisy, and knowing the 2-qubit depth gives a lot of information, because we can kind of think that the other things are almost perfect. Now the first utility scale experiment that was done by IBM in 2023, it had a 2-qubit depth of 60. Now the point is, now with Heron processor you can actually go up to 2-qubit depth of 100, but what is happening is that when you start folding, if the depth actually starts growing too much, you expect that almost there will be no valid signal that is coming out of that, right? Because when we try to extrapolate, we need some signal there. If there is no signal, if it becomes a white noise, then extrapolation will give me some rubbish answer. So what is done, a big solution that is done here is something called partial folding. The idea of partial folding, and that's why it is very important not to put a physical interpretation to lambda. Now I can say that why don't you do lambda as 0.2? It means is that you look into 10 gates, out of 10 gates you randomly select 2 gates and fold that 3 times. This is what lambda equal to 0.2 means. What it does is it restricts the size of the folded circuit significantly, and it makes ZNE useful for much deeper circuit. And the way we could do that utility scale experiment was by using this kind of partial folding. Good. There is one more challenge, and there is no immediate solution to that challenge. Let's assume that we have a Z type of observable, only Z or identity. Now, if I assume a depolarizing noise model, and sorry, I keep forgetting to change it. As P tends to 1, the Bloch sphere shrinks to the center, right? It becomes identity by 2, and if it is Z type observable, the observable goes down to 0. Now, let's say that I have a circuit whose original expectation value is 0, or it is very close to 0. Now what will happen if you even start doing this kind of folding? It was 0, it goes to 0, there is no fitting of that, right? You don't get what is noise doing here, because your original value was 0. As you start folding, noise is taking it to 0, so you don't really see what sort of gradient or whatever is coming here. That is not observable here. And therefore, if the expectation value of the original circuit is very close to 0, you can expect that ZNE is going to fail. And yeah.
Can you do like purification measurement to build up from rho equal to identity by 2 to somewhere? Like they do not purification.
Yeah.
So that kind of things can be done here.
Not that I can think of at this point. I mean, in practice, perhaps no. Yeah. So, and there is no immediate solution to this. If your original circuit has an ideal expectation value which is very close to 0, ZNE is not going to work. Now, there are some issues with ZNE. And if you have not seen this before, it's very difficult to immediately think of those issues. But you know, I mean, one of our very seniors say that there is a difference between doing science and being in an industry. What we do, even I did PhD sometimes back, not very long back, what we do, we kind of try to report the best results that we obtain. But if I am giving you a service, just telling that I have obtained this at some point, you can't obtain, this is not going to work. I need to make sure that my average is very good. That if I say that this is what you will expect, you should get something very close to that. Not that in some experiment I got lucky and got a brilliant result and you can never recreate that. This should not happen. Now, when I am doing partial folding, let's say that this is a previous Eagle device. Remember what I said is that we say 0.2, that means you take 10 gates, out of that you randomly select 2. Now let's assume that you have selected this gate and this gate randomly. I have selected this gate and this gate. What will happen? Noise in your selection is less, noise in my selection is more. Now I cannot expect these two results to be equivalent. So perhaps you will say that no, this works very well. I will say no, this doesn't work at all. So this cannot happen if you want to have a consistent performance. Question is, can you avoid this? Can you say that, okay, when you put your circuit on the hardware, just try to avoid these outlier gates. This is one possible solution that you can have. But the answer is that if you want to run really big circuits, that's what we want to do, to go to a scale where classical is struggling, where classical cannot go. At that scale where you want to use almost the whole of the hardware, then you don't have the liberty to say that I'll not use this gate, I'll use that gate. We don't have the liberty for that. And therefore, this kind of issue comes into play. The thing that is done to avoid this is something called probabilistic error amplification. So probabilistic error amplification, although I don't have this in the slide, but it comes with something called probabilistic error cancellation. That was the first thing. The idea was, let's assume, when I said that I don't know how to characterize lambda, I don't. True, it's going to be a tremendous job, and if you want to characterize lambda, you have to do a full tomography of the system. That's not possible. But what is done often in practice is, we assume that first, as we said, the single qubit gates are noise free. This is the first assumption. Second assumption is, whenever you have some interaction